Okay, so this is the week 9, part 2 lecture for Math 203. We're going to finish up chapter 17, critical IV calculations part 2, and then we're going to go over chapter 18, which is the amount to dispense and days supply. Okay, so titrated medications. Titration just means change. Adjusted. Medications that are titrated are adjusted over time or based on certain limitations or effects on the body. Heparin is something that you can consider as a titration because based on the APTT test, the adjustments might be made. So with titrated medications, we usually calculate they usually give you a range at which to administer the medication. And they want you to monitor the medication and change it as needed. They usually give you a starting flow rate. If they don't give you the starting rate, it's usually equal to the max or the minimum allowable flow rate. So the range they give you is the minimum and maximum. So you would always begin at the starting flow rate, which might be the minimum. Then you're going to adjust based on responses, and we're never to exceed the maximum rate. So if the patient's response exceeds prescribed parameters at minimum dose, discontinue infusion and notify authorized prescriber. If the patient does not have a desired response at the maximum rate, you should also call the prescriber. So using the previous heparin protocol for a patient that weighs 166 pounds, round patient weight and IV flow rates to the nearest tenth. So it says to calculate the loading dose, including the amount to administer. So remember, the loading dose was 80 units per kilogram, and on hand for the loading dose was 1,000 units per milliliter. So the weight's 166 pounds converted to kilograms. So the initial bolus is 80 units per kilogram times our 75.5 kilograms, which gives us a total volume of 6,040 units. So in order to administer 6,040 units, that's your D. The H is 1,000 units. Your Q is 1 milliliters, D over H times Q. So we're going to administer 6.04, round that down to 6 milliliters. The initial flow rate, according to our previous heparin protocol, the initial flow rate is 18 units per kilogram per hour. And the on-hand amount for the infusion is the heparin sodium 25,000 units in 5% dextrose and water, 500 milliliters, which the 25,000 over 500 reduces to 50 over 1. So the infusion rate for the heparin, 18 units per kilogram per hour. So first we have to find out how many units, so we multiply by the number of kilograms. So that's 1,359 units per hour. Now we have to find the flow rate. So we have the administration rate, the D rate as we called it, multiply it by the on-hand, the inverted on-hand, remember. Cancel your units, multiply across the top and bottom, do your division, and that gives us a flow rate of 27.2 milliliters per hour. Okay, so here is that heparin protocol. I just copied the parts we needed for these next few questions. So this question says the APT test was done after 6 hours. The result was 55. What is the bolus dose and amount to administer now? So we see when the result is 55, which is between 54 and 59, the bolus is 40 units per kilogram. And then the rate we increase by 2 units. So now the bolus is 40 units per kilogram, still the 75.5 kilograms. So that gives us 3,020 units. Now the rate, which was, So now we have to calculate the amount to administer. So in order to administer 3,020 units using our on hand for our bolus, which is 1,000 units per milliliter, D over H times Q, 3 milliliters. Now the new flow rate based on the APT test of 55 increase by 2 units. So the original was 18 units per kilogram per hour. Now we have 20 units. 18 plus 2 is 20. So we have an infusion rate of 20 units per kilogram per hour. So to find out how many units per hour, we multiply by the kilograms. So that's 1,510 units per hour. And again, this is like our D rate, the amount of medicine or amount of drug over time. So we have our D rate times our inverted on hand, and that's the on hand for the infusion, not the bolus. Multiply across the bottom and top and bottom. Reduce, and that gives us 30.2 milliliters per hour as a flow rate. Another PTT test, 69. So if we look back at our chart, 69, it's the same bolus. So the bolus isn't going to change. We're just going to repeat it. But now the infusion is going to decrease by 1. So if you want to, I calculated it again anyway, but it didn't change. So it's still the 3 milliliters. But the infusion, so remember, originally we started at 18, so after the first test we had to go up to 20, and now on the second test we have to go decrease by 1, or I'm sorry, increase by 1. So we went from 18 up to 20, now we go to 21. So now it's 21 units per kilogram per hour. Multiply by kilogram, we get our units per hour. So then we take our units per hour, multiply by our on hand, inverted, and that gives us our flow rate of 31.7 milliliters per hour. The next test, we get a result of 27, or 127, which is between 116 and 135. So here there's no bolus, and we're going to decrease the flow or infusion rate by 2 units per kilogram per hour. So remember, we were last at 21 units per kilogram per hour. So now we go down to 19 units per kilogram per hour. Multiply by our kilogram to get units per hour. Units per hour times our inverted on hand. And we end up with a flow rate of 28.7 milliliters per hour. Okay, so that was just a heparin, sort of a titration, but it was basically a heparin protocol we were following, making changes based upon the APTT test. And other medications will also be ordered to be titrated. A lot of times nurses will write up a whole chart based on the minimum and the maximum and calculate the flow rates ahead of time. This way they can do their tests. In this case, it is based on blood pressure. Titrate until effect. So if they do have to titrate, they automatically know what the flow rate is. So once you calculate one of them, you can use the same calculations to get the rest. All you're going to do is change this number each time because the weight's not going to change. You're going to do this table, if you choose to, for the same patient. So an order of xylocaine, 1 gram and 250 milliliters of dextrose. Start the IV infusion at 2 milligrams per minute. Titrate to absence of ventricular dysrhythmia. The dosage range is 1 milligram per minute up to 4 milligrams per minute. Now with this problem, the minimum is 1, but it actually starts our infusion at 2. So we'll go ahead and calculate the minimum and maximum, and then we'll calculate the starting rate. So the minimum dose rate or flow rate in milliliters per hour. So we take our infusion rate, minimum 1 milligram per minute. And our on hand is actually in grams. So we're going to use conversion factor to change that to grams per minute. And then we're also going to change that grams per minute to grams per hour using another conversion factor. Because we have to find the D rate in order to find the flow rate. So I just did it all in one. I just used two conversion factors using the dimensional analysis method. So 1 milligram per minute times 1 gram to 1,000 milligrams times 60 minutes to 1 hour gives us 60 grams to 1,000 hours, or 0.06 grams per hour. So we take our 0.06 grams per hour, multiply it by our on hand, and remember we invert that again because we want milliliters on top for our flow rate, and we get 15 milliliters per hour. So that was our minimum. Our maximum, if you notice, these are all the same. The only thing we changed is this number right here. The minimum was 1, maximum was 4. Calculate again, we get 0.24 grams per hour. So even this calculation is the same. The only thing we changed was the 0.24, and we end up with 60 milliliters per hour. So that's your minimum, your maximum, and now our starting. And again, the only thing I changed in this calculation is right here, the 2. The minimum was 1, maximum was 4, starting is 2. So 2 milligrams per minute, change it to grams, change it to hours, 0.12 grams per hour. 0.12 grams per hour, again, our on hand inverted gives us 30 milliliters per hour. So we calculated 1, 2, and 4. All we would need to do is calculate 3 and we'd have the whole table. So once you do one calculation, you can just keep your calculations, change this number and this number for each next calculation. Okay, order dopamine. Begin infusion at 2 micrograms per kilogram per minute. So notice this is now an amount per weight per time. So it's like a D rate, but based on weight. For bradycardia and systolic BP less than 90, increase infusion up to 10 micrograms per kilogram per minute as needed. You have a premixed bag of dopamine with 200 milligrams in 500 milliliters. The patient weighs 165 pounds. So we take our 165 pounds first, convert it to kilograms. So it says create a titration table starting at 2 micrograms per kilogram per minute and increase by 2s up to 10 micrograms per kilogram per minute. So here I've already filled in the table, and the next few slides have the different calculations. First we calculate the weight. So now we calculate the minimum, 2 microgram per kilogram per minute. So 2 microgram per kilogram per minute times our number of kilograms gives us the number of micrograms per minute. Now we need to convert that to milligrams per hour, basically because that is what we're calculating flow rates, so you know the time has to be in hours, and what we have on hand is in milligrams. So to convert 150 micrograms per minute to milligrams per hour, we need 2 conversion factors, minutes to hours, and then micrograms to milligrams. So using dimensional analysis, we end up with 9 milligrams per hour. So now that we have our D rate, we can multiply it by the on hand, Remember, and we do this inverted to get our flow rate. So the 9 milligrams per hour times the Q over H equals milliliters per hour. Do our division, and we get 22.5 milliliters per hour. So now we can use these same calculations, just replacing this yellow 2 here with 4, then with 6, then 8, and then 10. Each one of those will give you a new D rate. Then you take the new D rate and you would replace it in this calculation. And that's basically what the next few slides show you. I calculated them all out. Okay, so now this says you notice the pump is flowing at 35 milliliters per hour. What is the dosage that the patient is receiving at this time? So if we look back, oops, where did we go? The pump is pumping at 35 milliliters per hour. That's not on our chart, so we want to find out what the patient's receiving. How many micrograms per kilogram per minute is being pumped at that time? So you basically work backwards. We actually did this in the first part of the week 9 lectures for one of the problems there. So here we start with our flow rate. We multiply it by our on hand, but now the on hand is not inverted, to find the D rate. So if it's pumping or flowing at 35 milliliters per hour, we work backwards and we find the D rate right here in milligrams per hour. So the flow rate times the on hand gives us our dosage in milligrams per hour. And then we want to work all the way back to micrograms per minute. So if you have milligrams per hour, all we need are 2 conversion factors. One to convert our hours to minutes, and the other to convert our milligrams back to micrograms. Multiply across the top and bottom and cancel, and you get your micrograms per minute. So this patient is receiving 233.3 repeated micrograms per minute. So now we can actually find out how many micrograms per kilogram, because this 75 kilogram patient is receiving this many micrograms every minute. So if we take this many micrograms and divide it by the 75, that tells us exactly how many micrograms per kilogram per minute is. So, and it makes sense when you look at it. 3.1 micrograms per kilogram per minute, and it's flowing at 35. So it's actually between these two at 35, and we get 3.1 here. So it does make sense. Okay, so that brings us to chapter 18, which chapter 18 isn't really it's more common sense, I think. The amount to dispense, it's just the amount of medication needed to last a given number of days. And a day's supply is a number of days a given amount of medication will last. So, to calculate the amount to dispense, basically you need to know the amount to administer per dose, multiply that by the number of doses in a day, then multiply that by the number of days on the order, and that will give you the amount to actually dispense. So, order. Cephalexin, 500 milligrams by mouth 3 times a day for 7 days. And there are many different ways to do this. Just one method calculate the amount to administer using whichever formula you like. 3 milligrams, and we have 250 milligram capsules, or sorry, 500 milligrams. We have 250 milligram capsules, so it's 2 capsules per dose. Well, there's 3 doses in a day, so that's 6 capsules per day, and we have 7 days, so that's 42 capsules needed to fill the order. Another order. Furosemide, 80 milligrams by mouth every 12 hours for 9 days. We have on hand 40 milligrams per 5 milliliter oral solution. So the amount to administer per dose, D over H times Q, is 10 milliliters per dose. Number of doses per day is 2. Every 12 hours means there's going to be 2 doses per day, so that's 20 milliliters needed per day. And the order is for 9 days, so 20 milliliters per day times 9 days is 180 milliliters needed to fill the order. 35 units of Humalog, subcutaneous, 3 times a day for 90 days. 1,000 unit vials of Humalog, U100. So calculate the number of vials needed, and notice partial vials are not dispensed. So you're going to end up giving more than is actually needed. That's because you can't split up a vial. So we know we need 35 units per dose. 35 units per dose, and there's 3 doses in a day, so that's 105 units per day times 90 days. That's 9,450 units to fill the order. Well, it's dispensed in 1,000 unit vials. So we take the number of units needed, divide by the number of units per vial. So that gives us 9.45 vials needed, but we can't give 0.45 vials. We have to give a whole vial. So we're rounding up, so we give 10 vials to fill the order. Okay, now calculating the day's supply. So the day's supply is, you're basically calculating how many days a certain amount should last. So this can actually help you to recognize if a patient is taking their meds as ordered. Because if their medicine is running out beforehand, that means they may be taking too much. If they have leftover medication, then they may not be taking enough. So, to find the day supply, we take the amount to administer for each dose and multiply it by the number of doses in a day. Then we take the amount that is dispensed and divide it by that first number, the number of doses per day. We round that. Then we round the answer down to the nearest whole number. So, if we order Diltazam, 30 milligram tablets, well, if the order is 30 milligram tablets and we give 120 tablets, and it says take 1 tablet by mouth twice a day. So 1 tablet by mouth twice a day is 2 tablets a day. We have 120 tablets, so this should last 60 days. Ordered Tylenol, 120 milligram per 5 milliliters. We dispensed a bottle that is 150 milliliters. The order is 60 milligrams by mouth every 4 hours as needed. Okay, so 60 milligrams per 120 milligram, or 60 milligrams, and our concentration is 120 milligrams per 5 milliliters. So that's 2.5 milliliters per dose. every 4 hours is 6 doses per day. So 2.5 milliliters per dose, 6 doses in a day, that's 15 milliliters per day. So if we dispensed 150 milliliters, 150 milliliters dispensed, one day is 15 milliliters, right there, per day, 15 milliliters. So it should last 10 days. So 10 days worth of medication was dispensed. So if the patient runs out beforehand, that means they were taking too much. And that is the end of the week 9 part 2 lecture.